Today we continue with our renormalization of QED. Okay, so last video we determined that in total we have 4 different divergences, right? And we found out that with this redefinition of our Lagrangian, right, we can properly define these physical constants, both the mass of the electron and the physical charge of the theory. Of course, the mass of the photon we proved that is fixed at 0, right? Even under radiative corrections. And we also saw that by these 4 counter terms that I have right here, we can renormalize the theory and get rid of all these divergences. Right? So what we want to do today is to look a little deeper in the structure of the 3-point function of QED. Right? Essentially, the Ward-Takahashi identities still have some something to say about that, right? Besides what we already used it for when we were doing the power counting, right? So it fixed a lot of things for us, right? Lowered the degree of divergency of the theory in general, but it still there's some consequences of the Ward identity that we didn't explore, right? In particular, we were interested in this one. Let me write it. Right, one of the Ward Takahashi identity, which we wrote at the end of the generalized Ward Takahashi identities video, right, was this one. So we had this relation between the 3-point function in QED, right, and these 2-point full propagators. So this is the fermion propagator for momenta P plus Q. It's the inverse of the full propagator, and this is again the same thing, but for momentum P. And Q is the momentum of the photon going into this vertex. I can express this both in terms of Q or P plus Q, right? Or P plus P prime too. This is P prime right here, right? And in order to see how these puts constraints in our theory, right? Let's think on how these two things look, comparing the non-renormalized and the renormalized versions of the theory. So you could have this Lagrangian up here, right? This is the renormalized one, but I could also have just the first line with M and E replaced by M0 and E0, right? And of course the fields, I just remove all these R's here, which means the renormalized fields, right? So I want to see how this looks for the non-renormalized version of the theory, right? And I will define here a proportionality constant between this 3-point function in the non-renormalized version and, let me define it, the same thing in the renormalized theory. In principle, I could carry some kind of index for this, right? Renormalized, but I'll just call the renormalized one like this, because this is the one we'll be working the most in all the lectures. And this is the one I imposed renormalization conditions for, right? If you remember, by the end of last video, right, we said that this guy, we said that I define a condition for this guy, which was for some either P0 or P prime 0, or some Q0, which is the same, right, by conservation of momenta, right? This had to be equal to minus IE gamma mu, right? So this defines the physical charge, right, and the form of the vertex for a particular energy, right, this one. And now we want to use this relation, but it is important to remember that I use the physical charge here and the renormalized calculation for this guy. So this condition is on the renormalized theory, right? Now I'll have to see how this impacts this other guy and I'm defining a Z1. Also, in the previous lecture, I also defined a Z1, which is connected to this delta 1, right? I define a Z1, which is 1 plus delta 1 here, right? And at this point, it's hard to see that they are the same thing, right? Not necessarily, but I'll show that soon enough. For now, just the Z1 has no obligation to be the same I defined before. It will end up being the same, right? But I have to prove that. So one important consideration that we make at this point is that since this expression right here defines the physical charge for these theories, right, we have to choose this scale, right? But historically, right, most measurements of the charge of electromagnetism was done at very low energies, right? Here we talk about ultra relativistic theories, right? We are on high energy physics, right? But we know that most of the measurements for this guy, and to this day, the most precise measurements for this guy are made with quite long range experiments, right? Low energy photons, right? So it's very usual to impose this, to choose these guys, so that this reference point, remember, when we're doing renormalization conditions, you always choosing some particular reference energy when you define your coupling constant in, and then you know how to calculate matrix elements anywhere else, right? In this case, it's very the most common condition you find in books is this one. So Q0 is basically 0. So you're looking at very long wavelength for this photon, right? So what we're talking here is that we will impose that this guy, and now I'll forget P and P prime. It's easier to talk always in terms of Q0, right? In this case, and so I'll take this to 0, right? Let me write it like this so we don't forget which variable is 0. Right? This needs to be gamma mu. Right? And then using this definition, that means that this non-normalized version of the 3-point function needs to go to Z1 to the minus 1 gamma mu. So this is the expression we'll be using a lot today, and this one is the conditions. It is effectively the renormalization condition we'll be using for QED in all the next videos, right? Because it's very intuitive, right, to think of the charge as the one you measure at low energy, right? So in the non-renormalized version, the fermion full propagator, so I want to plug these into this equation up here now, right? So I need also to figure out how do these propagators look, right? I know how they look close to the one particle pole, right? So we have seen when we were looking at Shalin-Lehmann representation, right? The full propagator for a fermion near its one particle pole looks like that, right? You have a Z2, which is the field renormalization constant, right? And this is done with the physical mass. Remember, even before I do the renormalization to remove these factors of Z2 from the propagators, already I have the physical masses here, right? So I can keep them like that, right? And of course, there's some finite terms near this pole, but I don't care too much about them because I can take this equation near where these guys are going on shell, right? And that's what I'm going to do. So I'm worried now about a particular point. Let me copy this equation because I use it again. And I'm worried now about looking at this place where both P slash and P prime slashes are going to M, right? And Q mu is going to 0, right? In this region, right? Let me paste now the equation and I'll write it like that. The left-hand side here, since I have a Q mu here, it's approximately 0, right? But that doesn't tell me a lot. So I want to take the linear terms in Q. Right? And the very first one, it's minus IQ mu, gamma mu non-relativistic, right? Calculated at Q equals 0 times Q mu. Right? And of course, this guy, I can use this equation for. This is equal to minus no, there's no E here. Minus I Z1 to the minus 1 gamma mu. Right? The right-hand side, I have to write explicitly, right? I just substitute, take the inverse of this guy, right? And of course, near this point is just this term. I don't need the rest, right? This will be minus I Z2 to the minus 1 times, and so the first guy is P plus Q, so it will be P slash plus Q slash minus the physical mass. So this thing in the denominator comes to the numerator because I'm calculating the inverse of the propagator. And then I have the second guy that also has a term minus I Z2 to the minus 1. So I'll group them together. And in this case, I have minus just P slash. Again, minus M, so it's a plus M here, right? So this already is the difference between these two propagators. Now I can erase this equation, right? And here you see that there's some simplifications. So P slash goes away, M goes away, right? And I have only Q slash. So this becomes just minus I Z2 to the minus 1 Q slash, right? So I forgot a Q mu here. Yeah, this Q mu is wrong here. Sorry about that. Q mu should be here, right? It was multiplying everything. Let me put, otherwise this sign will be confusing, right? So there was a little mistake here. I just replaced this by Z minus 1 gamma mu, and the Q mu is just repeating, right? So I have Q slash here, Q slash here. You see the two equations are very similar, right? What I'm getting from the Ward-Takahashi identity at leading order in Q, right, is just this equation right here, right? Which tells me, of course, that and this is the first important thing we want to talk about today, that Z1 is equal to Z2, right? At all orders in perturbation theory. You see, I'm not doing the series here. I'm just taking the whole sum for these 3-point and 2-point functions, right? It's a full propagator and the full 3-point vertex. So this needs to be true to all orders in perturbation theory. And of course, that implies too, right, that since this guy is 1 plus delta 1 and that is 1 plus delta 2, assuming I've proven that Z1 is the same I did before. I didn't yet, but I will, right? But if I substitute this guy by 1 plus delta 1 and this one by 1 plus delta 2, and this is the same I defined before because it's the same definition, right? I also get that delta 1 needs to be equal to delta 2 in all orders in perturbation theory. And this is a very important, very important result, right? And we'll see why in a second. But before I do that, let me quickly prove that this Z1 is the same we used before. So the key point here is to remember that if you're looking at any S matrix element, what appears in your calculation is not the 1pi function, but really the amputated function, right? You're taking these whatever propagators here, which are going on shell, which are external particles, you amputate using the LSZ reduction formula, right? Usually I'm not worrying about this making the distinction between these amputated functions and the 1pi functions, because in the renormalized version of these theories, I remove this Z2 from the full fermion propagator, and I removed a Z3 from the photon propagator. But if you're talking about non-renormalized version of the theory, you have these factors of Z in your propagators, and when you do the amputation using the LSZ, if you go back to the video where I proved the LSZ, you see that you leave a square root of Z behind when you amputated. You amputate the propagator. So this guy, the amputated guy, right? Suppose I'm putting these three guys on shell, right? This will be equal to minus I E0 in the non-renormalized theory, right? Gamma mu non-renormalized, right, of Q, times, since you have two fermion propagators, you have square root of Z2, which is the field renormalization constant for the fermion, right, square, because we have two lines, and a square root of Z3 for this line here. For this line here, which you could put on shell, right? It doesn't matter really. If you can think of this line on shell, or think that line is connecting to some other vertex, which means in the middle you have a photon propagator that has a Z3 in the numerator, and you're taking square root of Z3 to each side, right? You're grouping the square root of Z3 with this vertex and the other one with whatever this photon connects to. So you can think of this vertex function in any of these two ways, right? You can bring a square root of Z3 here, or think you amputated the photon, is the same. And this is really the 1pi function, right? So if you think in terms of the non-renormalized theory, this is the sum of all the 1pi diagrams, but you still have this piece that the LSZ leaves behind. Now, suppose I want to compare this with the same thing calculated now in terms of other variables, which is what I get in the renormalized version of the theory. Right? It's the same thing, but I'm calculating in terms of other variables. In this case, this will be just now the physical charge and the renormalized version of the 3-point function. Now inside here, I have loops and counter terms and everything, right? And of course, I can compare those two, right? I can equate this with that, right? And what I'll get here, right, is on the left, on this part, I can forget this factor of minus I, because not contributing anything. I'll just write E0. Here I just have Z2. Here I have Z3 to the power half, right, times this function, and I need that to be the same as this, right? But of course, with the definition of Z1 I used in this video, this is just Z1 to the minus 1 gamma mu of Q, which is the same function I have on the right side here, right? Which means that I need E0 times Z2 times Z3 to the power half, and I'll send this Z1 multiplying to the other side. It needs to be the same as Z1 times the physical charge here. And of course, if you have a good memory, you remember that this is the definition I used for Z1 last video, right? So they are equivalent, right? Saying this guy is the difference between the 3-point function, the renormalized and non-renormalized theories, right, is the same as using this definition for the physical charge, right? When I defined that, when I defined that when I was rewriting my Lagrangian, right? So it's the same thing you can see here. Now, on to the consequences, right? So I said, now we know that we're talking about the same Z1 everywhere. Now I want to see why this is important. Either this one or this one, they contain the same thing. And it's easy to see if you think of a theory, right, that has more particles. So the first thing to notice is that if Z2 is the same as Z1 in this equation, I can write a much simpler equation for the physical charge, which is that the physical charge E is just the bare charge multiplied by Z3 to the power half, right? This is already very important. It's true at all orders in perturbation theory, right? And this tells me that the effect that will actually change the charge, right, from this initial value to the physical one is given by the Z3, which is the renormalization of the photon propagator. So it's really the photon, the changes going on with the photon once you go to loop corrections, that is redefining the charge in QED. Right? Why is that important? Right? Just try to imagine a theory where you have, I don't know, 3 particles coupling to this photon instead of just one. Right? We were so far in the very simple case where we just have the electron, but suppose there's more. Let's take 3 of them. So I have an electron which has electric charge -1 in units of physical E. Right? That's important. So I'll define all these the charge of all these 3 particles at some physical scale. In this case, again, I'll go to the limit of Q going to 0, right? And there they are all proportional to the same charge, as we know happens with all these particles. And the mass of the electron is just, I'll just call ME, the mass of the electron. So this is my E minus, my electron. Suppose I also have in my theory a muon, right? The muon is like a cousin to the electron, right? Has the same charge, all the same interactions as the electron, but it is much, the mass of this guy is much bigger than the electron mass, about 200 times bigger, right? Approximately. Don't want to be too precise here, I don't need to, right? So all the same interactions, but 200 times heavier, right? And suppose I also have a U quark, right? Now the quark has an electric charge too, right? Which is 2/3. So it's opposite sign to the charge of the electron, and it's a fractional charge actually, right? It's 2/3. And also has a different mass. This one is a little heavier than the electron, about 4 times heavier, right? And that's it. I have these 3 particles, but the quark also has other interactions, and that's important. Why? Right? Because with these 3 particles, of course, I have for each of them a full propagator, right? So 1 pi contributions that include loops in the propagator for these particles, right? So we have a Z2 for the electron. I'll have a Z2 for the mu, and I have a Z2 for the up quark. And they are in general different, right? Even these 2 guys, right? They have all the same interactions. So if you look at the loop calculation, it will be exactly the same. All the same diagrams, everything. But this mass enters that calculation, right? In the propagator. So of course, numerically, this number will be different from this. There's just no way, because everything is the same. Everything else is the same between the mu and the electron, right? In this case, it's even worse, right? The charge is different. and it enters these vertices, right? The first correction to all these guys will be something like these with a photon going here. So of course the mass of the particle goes here, the charge goes into these vertices, right? But the gluon is even worse because now the up quark also has gluons going on here, right? And of course you can expect, unless there's some conspiracy behind stuff, that these Z2s will be very different. Same is true for the Z1. You can think of the Z1 like there's something similar to the Z2, but it corrects this vertex, right? This bubble that goes around the vertex here, right? And of course, again, the masses of these guys enter here in the propagators that appear in there. So in general, right, I'll also have different Z1s for all these guys. For the up quark, right? In the case of the up quark, there'll be gluons there too. It's a mess, right? So now just think about it, right? If these Z2s and Z1s actually played a role in defining the physical charge, and this looks like it is the case if you look at this equation here, right? There's Z2 and Z1 here, right? So the physical charge gets influenced by Z1 and Z2, right? It would mean that even if I start with some boundary condition for the charge, the moment I look at some particular scale, in this case Q equals 0, right? Asymptotically low energy, right? If I calculate the electrical interaction for these guys, right? The electromagnetic interaction for these guys, away from that point, the matrix element for them would be receive finite corrections coming from these loops, and they would all be different, right? So I would lose this universality of the electric interaction. Away from that point I choose, I force them to be the same. I try to define a universal charge at one point, but the interactions are very different away from that point. And it's not just given by an overall constant for all of them, that I could say, well, I could incorporate these as a running charge. We'll get to that later, right? But the fact is that the electrical interaction would be different from these guys, and we would not be able to rewrite as a universal charge that is changing to all of these guys. But now if you look at this expression, right? This one, once you say that Z2 is equal to Z1, what you're saying, right, is essentially this other equation right here. But I could think of it like that, right? I just have E is equal to E0, right? Z2 for some fermion, right? Could be either of these guys, right? Times Z3 to the half over Z1 for each of those guys. And if Z2 is equal to Z1 in all cases, and that's what I just proven, right? This goes away for each of these guys. So they can have different Z2s, they can have different Z1s. That does not influence the charge, right? And this is guaranteed by the Ward-Takahashi identities, which are our quantum incarnation of the symmetry of QED, right? The global U1 and the gauge symmetry too, right? So you see, gauge symmetry, it's not even, and of course there's only one photon in this theory. The photon is receiving corrections for all of these guys. When I try to correct the photon, of course, the Z3 of the photon, let me write it here, the first contribution will be something like that, right? With as many loops that look like that, as there are fermions in your theory, right? So each of those fermions you contribute here, and Z3 is very different, and as a consequence, Z3 is very different in a theory that only has one guy and in a theory that has all of them. But in any case, this will all be incorporated in just one Z3, which is for the whole theory, right? The photon gets whatever corrections for the Z3 it gets. We already know that Z3 does not move the pole of the photon, but it does influence the renormalization of the charge in a universal way. So the symmetry is not only guaranteeing that I have only one coupling in the Lagrangian, right, but also that that coupling is corrected by loops, right, by radiative corrections, universally. So all the fermions will see that interaction being corrected in the same way, right? We'll see that translate once we try to incorporate that change in terms of a running charge, right? We'll see that there's only one charge running, and all the particles have charges which are proportional to that one thing that is running universally for all of them, right? I feel like I repeated the same sentence many times just now, but in many ways, but that's a very important point, and I wanted to stick, right? This is guaranteed by Ward-Takahashi identities. Now, there's one more thing we can say about the structure of this three-point function without going on to actually calculate the loops, which is what we're starting to do next video, right? And that is again because we have such strong constraints from symmetry here that we can guess a lot on how the corrections to the QED vertex will look like. So let's start by writing the most general thing we can for this function right here, right? We know it's a Lorentz vector, right? So this has only one Lorentz index here, and that fixes a lot about the structure, right? It can depend on these three momenta here, but I know that not all of the momenta are independent because I have a momentum conservation relation. I have this equation right here, right? So let's write it like that. It could be proportional to a Dirac matrix times some function, right? Which is a scalar function. There's no Lorentz index in it, right? It could have a combination of P prime mu and P mu, which is orthogonal to this one, right? And of course, it could also depend on this particular combination, which is Q mu. But for now, I'll just write it like this, P prime minus P mu, right? Times again some function of a scalar function, right? With no Lorentz indexes, right? I'm particularly interested in the case where these two fermions here are on shell and the photon is not, right? The photon is connected to a more complicated thing or an external field. So mostly what we'll learn today is about fermions propagating in an external field, and that's why I want to consider these guys on shell, and this is the photons being exchanged with whatever is the source for this external field, right? In that case, I know this guy will always be sandwiched between the spinor factors for these other two, right? So I'll have a matrix element, M mu, right? I'm here not considering the photon, so this mu here is of course contracted with the photon propagator that connects to the rest of the diagram, right? But this part is just minus I E, and now I'm working everywhere with the renormalized Lagrangian. You see here I have this function, this is the physical charge, right? I don't need to keep going back and forth because now I already know how the renormalized thing behaves, right? And I'll have the spinor factors for these two external fermions, right? So I'll have a U bar of P prime for this guy, right? I have this gamma mu in the middle, right? Because there's a spinor indexes here and U of P, right? So I have this product in spinor space, right? For a four-dimensional space. Right? And I know that these guys are on shell, so they satisfy these two equations. So if I multiply P slash to the right on this guy this will be just the mass times u of p. And if I have any p prime here and I multiply to the left, I also know that u bar p prime times p prime slash is u bar p prime times m. And that means that I can take any dependence in here on these p's and because just think about these guys, right? These guys in general, they could have, they need to have scalar combinations of the three momenta and Dirac matrices, right? So you could have something like p square, p prime square. You could have cross terms like q square, cross terms like p prime, or p slash. All of those could appear inside these functions a, b, and c, right? Those are easy to change for the mass of the electron, right? This is zero. This is no, this is not zero because my photon is off shell, sorry, right? So this is, I have to keep, right? This guy I can rewrite in terms, because I know from momentum conservation, right? This guy is, I can write in terms of q and the mass of the electron again, right? Just have to use this equation. I just take q square is minus 2p prime p plus 2m square, right? If I use this, I can exchange the dependencies on p and p prime by dependency on q square and mass. And the only thing left is p slash and p prime slash. Then I can eliminate using the fact that this thing will always be between u bar and u, right? And the conclusion of that is that I can say that A, B, and C, in fact, all of them, right, are just functions of q square. And of course the mass, but the mass is a constant, right, in my theory. The charge can appear there too, although I'm removing the charge explicitly in front. But, you know, it will only depend on q square, right? That's my point. I can exchange the dependencies on all the other momenta by q square. So that's true for A, B, and C. So now I can already limit, I'm limiting the most general form this thing assumes by saying that A, B, and C depend on q square, but I can go further, right? I know that this guy, again, what I'm doing for this guy is exactly the same I did proving the word identity. I just separated the photon line that is connecting this to the rest of the diagram, and I know that if I contract q mu with this thing here, this needs to be zero. This is just the word identity, right? And of course, this q mu will contract with this guy, right? Meaning that what I'm saying here is that u bar p prime times, now I'll just contract q mu to all of these, right? Right here. I'm contracting q mu to this equation and equating it to zero. I don't need the charge and anything because this is equal to zero. So q mu contracting with gamma mu here is just q slash times a of q square. Remember, now I won't repeat that, but a, b, and c are just functions of q square. Q mu contracted with these guys, I'll just write explicitly p prime mu plus p mu times b. And then the same in there, right? But remember, this is q, right? This right here is q mu, right? So this is just q square, right? Contracting this guy with that guy times c. And this needs to be zero. Now let's think about this expression just a little bit, right? This part right here is pretty trivial, right? This one is easier, right? Because I can just exchange this q slash by p prime slash minus p slash. And when I act with this p prime slash to the left, this will become the mass. this guy acting to the right will become the mass, and mass minus mass here is 0. So this whole term is 0, independent of A, right? This one in the middle is just, again, I can rewrite this guy as P prime mu minus P mu, and do the product here. This will be P prime square, right? The whole thing here will be P prime square minus P square. Again, these are both momentum for electrons, so it will be mass square minus mass square. That means that this is 0 independent of B, right? And I get this equation, right? Q square is anything because this photon is off shell, right? So C needs to be 0. Right? So this implies that C of Q square is 0, which now means that the most general form for my gamma mu is just little gamma mu times A of Q square plus P prime mu plus P mu times B of Q square, right? I got rid of the C. I can further simplify this using an identity called the Gordon identity, which is this one right here. I'll leave it as an exercise for you to prove this, right? But if I use this, now I can say, right? Again, I'm always thinking of this guy sandwiched between these two spinor functions, right? And in here, I can say, right, I have a U bar on the left. I can put this whole thing in here. And I'll have U on the right, right? U bar of P prime and U of P, right? But you see, because of this relation, I can take this part right here, right? Which is very similar to this one between these two spinors, right? And take and rewrite these as some function times a gamma mu. I just have to isolate these to the other side, right? Minus some other structure times this sigma mu nu q nu, right? Just use this Gordon identity to solve for this guy in terms of the other two. And then I group this part with this one, right? And see that the most general thing I can write, again, for some other function, right? I'm changing A and B, of course. But what I'm saying is that the most general thing can be some A prime. It's not the same because now it's getting contributions that come from this Gordon identity, but continues to be a function of Q square, right? Plus some other structure, which is sigma mu nu Q nu times now a B prime, some other function, right? B of Q square. And there's a usual convention used here, right? Which is, now I can make choices for this A prime and B prime. Of course, I can take constants out or put constants in, right? This is just conventional. And the one everybody uses, and you'll see pretty soon why this is useful, right? Is to write gamma mu in this way. Now I'm defining really these two functions. And I'll write it like this. So I have a gamma mu, and I'm defining a F1 Q square, which is in this case is just what I was calling A prime here, right? And in the other case, I pull out some constants of I, right? There's a sigma mu nu Q nu. I pull out a factor of 2 times the mass, and then I call this other guy F2 of Q square, right? And I hope by the end of this video will be clear why I'm using this parametrization specifically, right? And not another one, right? The important thing is through this whole calculation is to see there's nothing else besides these two structures. Here, let me make this, it's hard to read, mu, right? And that these functions only depend on q squared. And these guys are what we call the form factors, F1 and F2. Right? You'll see this is the form factors for QED, but the same idea of complex structures, momentum-dependent structures that can appear in vertices, right, is very generalizable. Right, so we talk a lot about form factors in QCD or hadron physics too, for the same reason. You have these corrections to what would be a simple vertex, just gamma mu in this case of QED, right? Now is being corrected by a function that depends on momentum and is introduced through loops, right? Or in some cases, for effective theories, it's introduced by the fact that the particle has structure, right? We'll see that when the time comes. Right? And there's a lot we can know about these guys, just thinking where they come from. So for instance, right, again, we're talking about QED, right? So let me paste this diagram again. And now if we think about the first contributions to these guys, right, these will be given by some line like that. I won't do the dashed because too much work to stop to put dash things here, right? And the very first contribution is just the leading order contribution is just minus I e gamma mu, right? And this guy is the sum of all 1 pi. I'm calling it 1 minus I e big gamma mu and parameterizing it in that way. And then there's corrections, right? The very first one is just a photon crossing right here, right? You have a loop that involves a photon and then of course propagators everywhere here. And you also have, of course, also a counter term that eliminates the divergences for that thing. Right? So there's a counter term here, right? Proportional to delta 1. But the important thing is that since at leading order in perturbation theory, so if I stop here, right, these two things need to be the same, implies conditions for F1 and F2, right? Clearly, if I calculate F1, I hope it's clear that these functions will have their own series in perturbation theory, right? But if I stop a leading order here means no loops, then F1 needs to be 1, right? Because these needs to be the same as that, right? And F2 needs to be 0, independent of the momenta, right? And remember, this momentum is the one coming through the photon there, right? So that's the first thing we can say. It's kind of a boundary conditions for these guys, right? It's a condition. Which means that in general, the form of these guys will look something like that. So F1 will be 1 plus delta F1 of Q squared. So this is what comes from loops, right? And F2 will be a pure loop contribution. So it only appears once you go to next to leading order, right? But there's more, right? Since these guys depend on Q squared, right? And I'm putting a renormalization condition for this guy, right? I said that I'll say that the full gamma for Q equals 0 is just minus I e gamma mu, right? That also tells me if I rewrite this guy near this point, right? Since F2 up here is multiplying by Q, This is a subleading contribution, 0 if Q is really 0. I'm only left with this one, so I can write now this thing as minus I E F1 of 0 gamma mu, and this needs to be minus I E gamma mu. You see, because F2 goes away. F2 is proportional to the momentum. And that tells me that at all orders in perturbation theory. Now, here I discovered something that is only valid as leading order for any value of Q square. And here I'm finding something that is valid to all orders in perturbation theory, but only for Q square equals 0. This guy also needs to be 1. It's another different constraint for F1. This one is independent of perturbation theory, but only for small momentum. Now, both of these form factors have really nice physical interpretations in the classical limit for the external photon field, right? So what we're thinking about here is of an electron being scattered by some external potential, right? And that can be written in the Born approximation as a one-to-one scattering, right? Which the matrix element is given by this equation right here. Let me write it. This is just conservation of energy for that guy, right? And this is 0 component of P prime and P, as opposed to a specific choice of P. This is really the Lorentz index 0, right? And this is equal to minus I E U bar P prime gamma mu Q of P, and some external classical, let me use CL here to represent classical field, that depends on P prime minus P, right? If you don't remember this, how to do calculations in these external classical fields, take a look at Quantum Field Theory 1 video 29, right? We did that in Quantum Field Theory 1, right? So I won't repeat everything here. So the first situation allows me to get information about this form factor, F1. And in order to get that, I'll assume that this classical external field is just electrostatic potential, right? So I have this guy that does not depend on time, so it depends only on the position, right? And is given by this expression right here. So just a static electric field, right? This expression. Since this does not depend on time, when I take the Fourier transform of this will become a mu classical. I could put a tilde here, but I won't carry too much notation. If it depends on Q, it means the Fourier transform of that guy. This will be 2 pi delta of Q naught, because it had no time here, times of a distribution in 3 momenta, right? And the rest is 0, right? And I can take these and go back to this expression, right? So the only surviving Dirac matrix will be component 0, because all of this is 0. So I can do this sum over mu here explicitly and write minus Im, and of course this 2 pi goes away with this one, the conservation of energy goes away on both sides, and I only get minus I E U bar of P prime gamma 0 U of P phi tilde of Q, right? Of course, this I put a gamma mu here, but it should be, for the full theory, it should be really gamma mu, right? Because I'm talking about the whole thing. Otherwise, there's no F1, right? So that's the full gamma. Now, if I think that the shape of this electric potential here is changing really slowly, right, with position over macroscopic distances, right? I don't want to take it constant, but suppose it falls down really slowly. That means that this Fourier transform will be picked around Q equals 0, right? It will be a very sharp distribution centered around Q equals 0, right? Because in the limit, this is independent of position, this becomes a Dirac delta in Q equals 0. That means that this expression will be dominated by small values of Q, right? And we know, because of our conditions, that if Q is going to 0, this guy now, gamma 0, is going to gamma 0 F1 of 0, right? From this thing right here, right? So I'll substitute that here. I'm assuming my potential is falling over macroscopic distance, so I can do that substitution and write that this is Im is equal to minus I E F1 of 0 U bar P prime gamma 0 U of P times this distribution. Copy here, right? And of course, in the Born approximation, as I said before, I can equate this to a scattering through a potential, right? The expression in this relativistic normalization I'm using is that this is equal to minus 2mi times this momentum space potential, right? So I'm doing the non-relativistic approximation for this as a scattering to a through a potential, right? In that non-relativistic limit, right? Again, in that video 29 for quantum field theory 1, we proved that in the non-relativistic limit, you have to write U bar and U explicitly, and you can just show that this is equal to 2m psi. Of course, there's some index for the spin. Let's call that S prime dagger of P prime, right? And psi S of P, right? This is just the non-relativistic approximation for this term here. And of course, there's some completeness relation, which tells us that the spin does not change in that limit, right? There's just delta S, S prime. This S is the spin of this fermion, and S prime is the spin of that one. Comparing these two relations, I can get the potential, right? And then do a Fourier transform for that potential. I go back to this guy, right? I'll just do a Fourier transform on phi tilde and go back to phi of x, and this will be just v of x is equal to E F1 of 0 phi of x times this delta of spin, just not flipping spins at this approximation, right? Which gives us a nice interpretation for F1, right? F1 is essentially the charge of this fermion, in this case the electron, right, interacting at that vertex, right, in units of E, right? And of course, if I go away from Q equal to 0, this function starts to change, right? F1 starts to be different from 1, right? And that means that the effective charge I see, if I'm doing scattering by this potential, will be this product, right? So it's clear that this is just an electric interaction, but you get corrections as you move away from Q square equal to 0. Now we want to see that both this function F1 and F2 also contribute to the magnetic moment of this fermion, right? And in order to look into the magnetic moment, of course, we have to choose a different external field, right? Now I'll take my external classical field to be given, again, is a static potential, so it does not depend on time, right? But now it will be a vector potential, right? This one. Because of course, this generates a static magnetic field, right? So now, going back to our expression, right, this IM that we had before is the same thing, right? But now these three components are different from 0, and this one is 0, right? So now I'll have IE U bar of P prime times gamma I. I goes from 1 to 3, it's just the three space coordinates, right? U of P, A, I. And here I raised this index, so be careful, there's minus that disappear from here because of that, right? Classical of Q, right? I'm not consistent with these tildes. I'll leave it there, right? And then I can rewrite this, right, as I E U bar P prime times the whole thing, right? It's not easy to just get rid of a part of it, right? I have to look at the whole thing, which I'll write right here, sigma I nu. So nu is going from 0 to 3, and I is going from 1 to 3. Q nu over 2m f2 of q squared, and then this thing, right? Again, I'll do the same thing I did before, right? I assume this distribution peaks near q equal to 0, right? And I'll take the non-relativistic limit for these guys. But now I need to be more careful, because in the limit q really is 0, this is all 0, and then I get nothing, right? So I want to do it carefully to get the linear terms in q, right? And I'll start with this part first. Then later I look at this other piece right here. So in the non-relativistic limit, I will approximate these guys, sorry, like that. So this is the square root of P scalar sigma, square root of P scalar sigma bar, psi. If you don't remember these classical solutions to the Dirac equation, go back to quantum field theory 1 and take a look, right? And this is approximately square root of m times, now I'm keeping, right? I could throw away everything, but I'm keeping these momenta here, because eventually I want to write these all in terms of q and keep the linear terms in q. So it's psi, and this one is this, 2m psi, right? So I want to put these guys here and here, this expression here and here, right? And do the product with these Dirac matrices in the middle here, right? There's a little bit of algebra to be done there. I won't do everything, right? But the point is that I can rewrite this. I'm only worried about this piece for now, right? So this structure that is showing up there, can just by putting that and throwing away everything that depends on the momentum square away, you get 2m psi prime. Psi prime here means that it depends on p prime and s prime. So it's the spin of this particle. Just simplify by writing psi prime, right? And in the middle here you get p prime sigma over 2m sigma I plus sigma I p times sigma over 2m psi, right? So this is just doing the products there. and using a little bit of properties from Pauli matrices, right? Now, I want to rewrite this as something that looks like that, right? And will be clear soon why. I want to group these two pieces, right? And the way to do that is to use this product here. I can just write this as a p prime, say j, because it's sum here, right? P prime j sigma j times sigma I. And that's, of course, just using properties from the Pauli matrices. This is P prime j delta ij plus P prime j I epsilon, right? This is the totally anti-symmetric Levi-Civita tensor, right? J I k sigma k, right? And I can do the same for the second part here, right? I'll get pj sigma I sigma j in this case, because I is to the left. That becomes pj delta ij plus pj I epsilon ijk sigma k, right? And then if I add those two terms, right, this becomes just p prime I plus pi minus I epsilon I j k sigma k, right? I have to exchange these here. There are relative sign, right? So that is p prime j minus pj, which of course is kq, is qj, right? Which I wanted, right? I want terms linear in q, and that's how I get them, right? This, if I go back now up here, right, what I'm saying is that this guy, let me repeat it, can be written as p prime I plus pi over 2m minus I epsilon I j k sigma k over 2m q j psi, right? So I have these two terms, and they are both coming from the f1 part here, right? This is all multiplying f1, right? Because I'm just rewrote these Dirac matrices between this U bar in a very complicated way. The point here is, since I'm interested in the magnetic momentum of this fermion, I don't need to worry about this part, right? Of course, there's an interaction. Since I have a fermion moving in an external magnetic field, of course there's an interaction that depends on the momentum of this charge, right, moving in a magnetic field, but it has nothing to do with the magnetic moment, right? This is diagonal in spin. It does not even depend on the spin of these particles, while this part does, right? This part here does, because there's a Pauli matrix here that can rotate the spin and all, right? So I can forget this part because it won't be important for the effect I'm trying to see. So I'll stick with the other one, right? And now I write both terms. If I go back here, let me copy it. So let me take this whole thing here and move down here, right? This is just I am, right? And now I have these two parts. Let me move the one that depends on F2 down here. And then later I'll put them back together, right? So these I just repeated down there. So this is summed. And this part now I exchange by this expression I just wrote, right? Of course, I already used u bar, and u, so this is psi prime dagger. This is just psi. And then I have this part multiplying this thing here. Let me put like that, right? And then remember, I'm looking, assuming this is dominated by q, small q, right? Since I already have a linear term in q here, I can take q equal to 0 in this guy, right? And there's a very similar situation here, right? In this case, I already have a q here, so I can take q squared equals 0 here, right? And inside those spinors, I can do a rougher approximation. I don't have to keep the linear momentum terms here because already there's explicit momentum outside, right? So I can rewrite this part, right? Just using the most simple approximation for this guy, which is just 2m times size and all of that, right? It's similar to what I did in the electric field. So let me just repeat this piece here. And I'll rewrite the F2 part doing the same approximation. So I keep this IE here. This one becomes 2m psi prime dagger, just the non-relativistic approximation for this product, right? In the middle, I have this guy right here, right? And I can actually do this product, right? This product, let me write it here. I can do this thing, sigma I nu q nu, right? Using the definition of this guy, right? So the first thing is that I already took q going to 0. There's q0 0, right? Minus sigma I j q j, right? Of course, because I0 is 0, right? Sigma I0 is 0. Right? And that I can write as minus I over 2. And this guy is just a commutator of gamma I gamma j times q j, and that I can write explicitly in terms of Pauli matrices, right? For the convention I'm using for the Dirac matrices, these guys are just Pauli matrix in this way, right? So if I do it explicitly, this becomes just minus epsilon I j k sigma k q j, because you have commutators between Pauli matrices here, and that's where the epsilon comes from, right? And of course, this is multiply the identity in this spinor space, which allows me to contract this guy with that times a delta of spin, right? So no, I cannot do that because of the sigma here. So yeah, never mind that. I'll just get yeah, this identity is spinor space. Okay, so if I do that here, right here, I can rewrite this piece in the following way. There's a minus here, so there's minus I epsilon I j k sigma k over 2m k j, right? F2 of 0, right? So first I just use that to get all that part, right? F2 of 0, and on this side I have psi, and again the same field, right? So this is my IM, right? And now I want to put these two parts together. You see they look very much alike, right? I have just F1 plus F2 here essentially, right? But I want to reorganize stuff, so I'll write everything in this way. I have a I'll bring a total minus sign to the front. This minus I over 2m times 2m charge from here, psi prime dagger. And now in the middle I have this combination of these two terms, which I'll write like that, just 1 over 2m, right? I'll take this Levi-Civita and this Pauli matrices outside, right? You'll see in a second. So I'll just keep sigma k f1 of 0 plus f2 of 0. And then I these indexes, right, minus I epsilon I j k q j a to the I classical of q, right? And now I have something pretty nice. I forgot the spin. Let me move this to the right because I forgot this psi here. Now, if we look at this, I have a part here. Let's paint that in green. I have a structure that you might recognize here in purple, right? In pink, and then every the spin structure right there, right? With an operator that actually can interact with the spin. This thing, right? If I lower this index, that changes a sign in here, and then I exchange J by I here, and rename I and J, you recognize this as just the magnetic field, right? This is the K component of static magnetic field in momentum space, right? Because this is just giving me the rotational between, right? So that's the first part, right? Yeah. Of course, since this is in momentum space, I have a momentum here that becomes a derivative if I go to position space, right? And this guy, right, I'll just call, in fact, a combination here. Let me write explicitly, and then I'll say what I'm calling the magnetic moment, right? I can rewrite this guy as I am, right? And here I'm defining something. So let me put it like that, right? That's 2mi, which is just this piece, right? The spin part, psi prime dagger, right? Times, and here I'm defining this magnetic moment, momentum k, right? Times b tilde component k, right? Psi. And then just comparing these two, you see that the way I define this guy is mu k is equal to E over m. So I absorb the charge, I absorb the factor of m here, right? Times f1 of 0 plus f2 of 0. And I took a factor of 2 here and grouped with this Pauli matrix, because of course this is the spin of the fermion, right? This is the spin of the electron going there. So these two expressions together are really important, right? I can take these a few steps further by again comparing these with the Born approximation for a scattering in a potential, right? Just equate these to minus 2mi again v tilde of q, right? And then I conclude that this v tilde, right, will be just minus mu k, right, times v tilde of k, right, where you know this expectation value means I'm contracting this guy, this sigma, with these two spin variables, right? Which is exactly, right, again, this I hope you recognize is what you expect for the interaction of a magnetic moment with an external magnetic field, right? There is a parametrization we use usually for this guy, right, which is rewriting the magnetic moment. This is for a particle of magnetic moment mu, right? There's a usual parametrization for this guy is to write it in terms of a G factor, which I'll define here in this way. So this is a definition for G. Spin of the particle, which of course for the spin half fermions we're dealing with is just sigma over 2, right? So just comparing, this is the G factor. Just comparing these two expressions, you see that G is given by 2. Of course, F1 of 0 is just 1, as we saw before, plus F2 of 0, which is 2 plus F2 of 0, right? So you see that at leading order, right, this magnetic moment of this particle will be given for G equal to 2, right? And that's the prediction you would get since you're not including any loops. Remember, F2 is 0 at, oh, I forgot a factor of 2 here, right? There's a 2 here and here, right? So of course at leading order, this is 0, right? And that was the prediction of a Dirac equation, that these particles should have a G of 2, right? But in the 40s, right? In the 40s, people were already measuring these G, and there were strong indications that that it was not 2, it deviated from 2, right? And so it was a huge success for quantum field theory when people finally calculated the loop contributions to this factor and saw that this correction coming from F2, right, actually corrected G away from 2 and agreed with the experiment, right, which is, again, one of the earliest successes of QED, right? Very, very important result, historically speaking, right? So you see that loops don't only give us headaches with infinities and all, right? There's physical effects that are encapsulated in them. We know, usually nowadays, you hear a lot of G minus 2, because of course, if you subtract 2 from here, you're looking only at this loop contribution coming from F2, right? And that's a measurable quantity and a very, very important prediction coming from really quantum field theory, right? The loop effects. And again, this is also nice because already we didn't calculate those loops yet. We know that the 3-point functions diverge, right? But already here we see at least some part of this 3-point function is directly connected to an observable, right? So you can already guess that F1 might hold the divergences, but F2 must be finite because it's really almost a directly measurable quantity, right? And we'll see that. We'll calculate these guys at one loop explicitly, and you see that F2 is finite, and we can actually calculate G minus 2 of the electron in QED, right? But that's something for the next videos, right? See you then.